Well, today we're very lucky to have Erich Poppitz sort of visiting us from Toronto. Wish it was in person, but this is still awesome. And Erich will tell us about confinement and strings and so on. Thank you, Erich.
Yes, well, thank you very much for having me. It's always a pleasure to talk in Minneapolis. One thing you don't have to worry is about finishing on time, so it's wonderful. So yes, I'm going to tell you about this work, which is really a summer project for two very bright undergraduates, Matthew Bupp and Sam Wong. And it's a wonderful thing now of this Zoom era that they can be both here. And as a matter of fact, some of the details of the work I'm not really privy of, so they can help me out if there are questions. In any case, so this is the main thing about the work. And I will also use some results of older work with Andrew Cox and Samuel Blanc and Mohamed Amber and Tin Suleiman Passage. Okay, so in a way of motivation, I will just use the title to motivate things. Okay, so motivation is, first of all, the study of confinement. Confinement is an old and difficult problem in quantum field theory, and there are very few settings in continuum field theory where we can actually study it in a controllable way. So the second part of the title is R3 cross S1. And this is one of the few non-perturbatively calculable setups in quantum field theory. It was a development really started by Mithat Unsal quite a while ago, and many other people have worked on it. And many features of quantum field theory on R4 are believed to be continuously connected, that is to say, without phase transition in some classes of theories, to features that you see on R3 cross S1. So it's of interest to study properties that you can actually calculate in a believable way and see what you learn. Now, admittedly, many people here have studied confinement in many different settings. And right away, I should say that the confinement in this theory that we shall study is not quite like the confinement that occurs in theories in R4. So confinement has an abelian nature, so it's different. Nonetheless, it's interesting to study. I mean, obviously one motivation is because you can, okay? So it's a serious motivation. And there are nuances in this abelian confinement that we'll see, which are not shared by other models of abelian confinement, for example, like cyber-Quitten theory. And this confinement captures many aspects of the 4D theory, even though the theory is compactified. And moreover, future lattice studies of confinement are much more likely to occur in this setup than, for example, in cyber-Quitten theory, where it's totally a dream to ever put it on the lattice. So it's interesting, and so I think it's a worthwhile topic to do. And the double string collapse is in the title because it's our most unexpected finding. I will describe it to you, and I don't know what to make of it, okay? But it's a strange feature. I don't know how to understand it analytically, but we're pretty confident it's true, okay? And of course, after all this motivation, there is another one. After all, this is quite a fun thing. And at least in Canada, when you write that on a grant application, they give you money, okay? I don't know about the US, but I put that as a main motivation and it works, okay? I can say that, okay? So that's my motivation. Okay, a little bit more detail. Confinement is the fact that if you have, for example, a theory of pure glue and you introduce quark sources, the color flux tube, the color field does not go to infinity like it would in electrodynamics, but there is a flux tube forming and there is a linearly growing potential between the two objects. And what is interesting about R3 cross S1 is that there are various classes of theories where this phenomena can be studied analytically. So I must say that in this talk, I will just state what the properties of these theories are, because I cannot possibly dwell into the details because theory with 4 supercharges. I will consider it compactified on R3 cross S1 with periodic boundary conditions on the S1. And I will consider the direction, the S1 direction, to have size L, which is much smaller than 2 pi over NL. And this is the condition that allows us to calculate in this theory. And just qualitatively describing why that happens is that in this limit, the theory abelianizes. The gauge group breaks itself to the maximal abelian subgroup at a scale 1 over Ln. And when that happens, if that scale is much bigger than lambda, it's pretty clear that the coupling is weak. There is no charge matter under this Cartan subalgebra. So there is a weakly coupled theory, which is 2 + 1 dimensional at long distances, and it's semi-classically calculable. So it's quite an interesting setup. So
Eric, just about motivation, I'm trying to follow that. No, you mentioned this periodic boundary condition for Fermions, or what you mean?
Periodic, yes.
But okay, because associated with this, say, if I think in terms of R3 over S1 as kind of small circle, right? Then I would say that it's kind of analog of high temperature, or can I think it this way?
No. It's a spatial circle because the fermions are periodic. You can, if you want to think of
how you differentiate spatial circle from time circle?
By the boundary conditions of the fermions.
No, just a moment. If you consider high temperature, it would be R3 plus multiplied by S1 still. With
the fermions would be
anti-periodic boundary condition. I agree, but when it's not periodic boundary condition for fermion, it's not about partition functions, then it is an index.
Yes, you can say that for the
right. Which is
the
very
partition
different.
function is the Witten index. Is correct. Yes. But
but then to call it confinement, I think it's not very much appropriate.
Oh, I think it's very appropriate. I mean, I can look. I mean, I can slice my Euclidean R3 cross S1 any when I want. Okay, and I can declare that the time direction is not along S1, but it's along R3. So it makes a lot of sense. It makes perfect sense.
It also preserves supersymmetry. If you
I agree.
The thermal partition function, you lose supersymmetry.
No, I agree. Of course, no, that's true. But Misha, I agree with this. And it is kind of, in certain sense, it's definition of the index, right?
Yeah, but he is not going to calculate the index. Of course, it's in order to calculate the partition function with this boundary condition, you calculate the index.
Absolutely.
But that's not what he wants to calculate. He wants to calculate some other.
Yes.
Okay.
Yes, I want to study other properties. Okay.
Okay.
Welcome to Minneapolis. I love you guys. Okay.
No, I'm sorry, but
it's wonderful.
Look,
okay.
But look, if I would not ask, then you would think that you are not in Minneapolis.
Exactly. Yes. Exactly. Yes. So, so I want to say now that in all our studies, we will study the long distance theory. So we will ignore the dependence of the fields on the compact direction, even though it's potentially very interesting. So if I insert a QQ bar pair, then a confining string is like a line in R2, a static source, just to remind you of that. Okay. So this is my motivation, okay? So let me start by summarizing the results, okay? And then I will go on, okay? So the first result is this, that if you consider static quarks of general N-alities, so you can consider fundamental, anti-symmetric, whatever, okay? Of general N-alities, they are confined by, the strings are not lines in R2. Rather, the strings are these double objects, okay? Two strings objects, we call them double strings. And this theory turns out to have a number of vacuum, which I will review. And there is a given vacuum outside and a different vacuum outside, so inside. So there are two domain walls that form such a configuration. And this is how the confinement mechanism proceeds, okay? I will explain that in great detail. I just want to mention one thing.
So what's different with the Polyakov picture? What's the difference? The presence of fermions or what?
The presence of fermions, yes. And dynamically, I don't want to discuss that because it's another talk. The mechanism of confinement is a magnetic baryon condensation, as of course you know very well.
Yeah.
It's not monopole condensation. And magnetic baryons have more than the minimal charge, which means that these objects carry only part of the fundamental flux rather than the fundamental flux.
Yeah,
that's the main thing, okay? I can put it in different ways, but that's what it is, okay?
Yeah, non-abelian strings are arranged in the same manner, right? In 4 dimensions. Non-abelian strings couple monopole to anti-monopole, but you need 2 of them in order to carry the full flux, magnetic
Exactly.
flux.
Yes. So I was going to make a comment on that, but yes, I will make it now. So we argued for this mechanism already in 2015 with Mohammed and Tin. But what's interesting is that at that time we didn't understand that there is some symmetry structure in this theory, which is very rich. There is a mixed anomaly between the discrete chiral and the one-form center symmetry. And as a matter of fact, this anomaly implies that quarks are deconfined on domain walls. So in some sense, you can argue that the mixed anomaly between the chiral and the center requires this picture, because you can take this string and open it up. So then you obtain two quarks. They hang on a domain wall. There is one vacuum. This vacuum is the upper vacuum, and this vacuum is the lower vacuum. These two walls actually have the same tension because they're both BPS walls. And these quarks can move like this without any cost of energy. So quarks which are confined in the bulk by such configurations, when they end up on the wall, they're deconfined. So it's a very interesting story, okay? We did not know at the time. Yeah.
Is it one and the same wall in the middle and outside?
No, they're different walls, but they're both BPS walls. And they both have the same tension. They're different BPS walls.
But if they are different, there is not necessarily collapse. They may not collapse necessarily. Maybe.
No, what do you mean collapse? No. What do you mean collapse? These quarks have no force between them because this tension and this tension is the same.
That's okay, but you know, in order for them to fuse into maybe you can wall anti-wall, two walls.
We haven't gotten to the fusion yet. That's further down the talk.
But you see, in the standard, similar situation occurs in four-dimensional Affleck-Dine-Seiberg superpotential. If the gauge symmetry is SU2, there exist two distinct walls.
Yes.
And therefore, you can form a kind of your figure out of two distinct walls. But we don't know whether they collapse or not, because if you start pushing them together, you come to the point where superpotential becomes infinite, and they are may not necessarily penetrate through this superpotential, so they are still separate.
Exactly, but the difference between that theory and this theory is that in this theory on R3 cross S1, the walls are totally semi-classical. You never go through any infinity. That's really.
Eric, R3 theory by itself is not weak coupling, right?
Oh, it is. It's an
small,
abelian theory.
Small radius, everything is at weak coupling.
It's small radius. I will write the Lagrangian.
No. Consider just three-dimensional theory. Are you saying that three-dimensional theory is in the weak coupling?
Not at all. No.
But if I have
no, but you see, this is a three-dimensional theory, which is abelian.
The limit like S1.
It's abelian.
Abelian, yes, yeah. Abelian, I agree, but original SU2 or whatever, it's not abelian, right?
Of course not. But what happens is that the holonomy gets an expectation value, and it breaks this to U1 to the n-1. So in this theory, in this limit, it's abelian.
All non-abelian, non-Cartan generators get
everything
a
is heavy,
mass, and they are not excited.
No, right. But then it's close to what Misha mentioned. Misha, you mentioned about Affleck-Dine-Seiberg. I agree, but even there, for example, in four dimension, it was a function of to get to this regime there. With coupling regime, you needed to consider, light quarks, right? That the mass much smaller than lambda, right?
Yeah, but if you want to these walls, to these two distinct walls in SU2 gauge theory, if you want for them to come close to each other, you are necessarily at least part of this wall here. And here is separated. There is a point where in the between where the superpotential is infinite.
I agree.
Remember, the superpotential phi plus 1 over phi. So this infinity, we don't know how it is resolved because it forces us in order to come here.
Mish, I agree with this. No, but what I'm trying to ask it's a little bit different question, because what I'm trying to say is that in abstract Dirichlet, to be in big count, you need this parameter of the theory must be much smaller than lambda.
Yes.
Yeah, even if you take mass small, but you want this wall to come.
No, I agree.
Then most of the field, they are weakly coupled, but not when you come close to the 0.5 equal to 0.
Okay, no,
it's all true. But can I continue with this theory?
Yeah.
Well,
I'm only summarizing the results, guys. Let me give my talk, okay?
Go ahead.
Okay, so I was just making this comment about anomalies. That's a very interesting connection, okay? And because of that, I want to also mention these double strings and deconfinement on domain walls also happen in other theories on R3 cross S1, which are not supersymmetric. You know that Mithat taught us how we can study other theories on R3 cross S1. And they also have mixed 0 form, 1 form anomalies without supersymmetry. And this double wall structure is very generic. But here I just study super young mills. I'm just saying that, okay? So that's the result number one. Result number two is very strange, and I don't know what it's trying to tell us. Okay, you'll see when I explain it in detail. But what's interesting is that quarks of all N-alities are confined by such configurations, but only fundamental quarks for n bigger than 4 are confined by a single string. In other words, for fundamental quarks for more than 4 colors, these two strings form a non-BPS bound states, so they attract. In all other cases, they repel. And we understand that numerically. We have performed many checks, which I will tell you what they are, but it's a strange property and I don't know what it's telling us. But anyway, that's a result, which I will explain.
Excuse me, when you speak quarks in the fundamental, this is in addition to the adjoint fermion.
Oh, these are just static Wilson loops, Misha. These are just static sources. Yes, yeah. So this is a theory with a center symmetry. I'm just probing it with quarks. Yeah.
So you mean that it is quarks which there is no quark, it's just external parameter.
It's very heavy, yes.
Yeah,
heavy. Yeah, very heavy. Yeah, absolutely, yes. But there is this difference between different kinds of quarks. And okay, there is this property which I don't know why it happens. It's trying to tell us something, but we haven't figured it out. We also don't have a simple understanding thereof, but maybe you guys, because you know so much about BPS domain walls, maybe you'll have a thought about that after I tell you how it comes about, okay? So the third thing is that something that people study in general in confinement, they study the analytic dependence of string tensions. And there are various scaling laws for the ratio of the K string to the one string tension, known as the sine law, Casimir, etc. Okay, so people have proposed them in Cyber-Quitten, in M theory, etc. Okay, and it turns out that this theory has the weakest analytic dependence of all. It's almost flat. It's very strange, and I will explain that. That I can explain qualitatively easily. So we'll show that, and we'll also study what happens to this analytic dependence as we increase the size a little bit. We have some leeway to include W boson loop corrections, which give us some sensitivity upon increasing the size. And so my point, my goal in this talk is to explain this and address all your questions. But before that, let me just say one more thing, and that regards the tool we use. A lot of the work we do is numerical, and the we is used in a very generalized sense. It's my collaborators that did all the work. They use this supercomputer, and they used about 15 core years of that. And I just want to tell you what theories we studied. So we studied quark anti-quark sources with N-alities from 1 to n/2 for colors from 2 to 10. And for each source, we studied separations from 5 to 100 or 200 in units of the confinement scale. And for each such configuration, you have to monitor how big your grid is, etc., etc. And then in the end, you repeat everything, including these W boson loops for 2 different values of the size of the S1. Okay, so it's quite a bit of numerical work. And of course, I don't know all the details, but I just wanted to give some credit for that. Okay, so this is my plan.
I have a naive outsider's question. Does your previous results, the summary you find, depend on how many families of the quarks you introduced?
Oh, the quarks are it's a good question. The quarks are non-dynamical. You see, this is like, imagine a pure glue theory. and you're just studying static quarks. So the quarks are non-dynamical, so it's a non-issue.
Call them
Okay.
probes. But
Probes.
a physical question: how small was the radius of the compactified dimension compared to your, well, to your parameter crucial lambda n? I mean, so that if it is not small, then it's a strongly coupled theory, right?
Yes.
It has to be small.
So I don't want to go to my last transparency, but in the case when we included this W boson loop corrections, we allowed ourselves to sin a little bit. So the size was not much smaller than 1. So the ratio lambda NL over 2 pi, which is the small parameter, could be as large as 0.6. Okay, so okay, but nominally it was very small. But while increasing L, we went to 0.6. Okay, take it or leave it. Okay.
Can I ask a question as well? Sorry. Yeah. So how big was the separation between test quarks? And what I have in mind is, was it large enough that you would expect pair production of doubly bosons?
No, never.
Okay.
Never. Yes, yeah. We
Okay.
did.
Maybe I'll ask more about that later, but we talked about it before.
Yeah. Okay, so, all right. So this is my outline. I will review this theory in this limit. I will just review the effective theory. I will not derive it because it's another talk. Okay, I'm happy to talk about that, but okay. So I will use.
Remind, please. L is the distance between quarks, or
no. L is the size of the circle.
Okay, so I'm checking that. Okay, and lambda.
Lambda is the strong scale.
Strong scale defined in four dimensions.
In 4 dimensions, yes. Yeah.
I see.
Yeah. So yeah.
Okay.
And n is the number of colors. Okay.
Yeah.
So I will review this theory very quickly. This theory has been known for a long time, since 1996, and elaborated upon since. After that, I will explain the argument for double string confinement, and I will talk about what objects confine quarks of general weights. I will present the numerical results, and then I will talk about string tensions, N-ality dependence, and finally talk about increasing L and discuss that. Okay, so this is the part where we may go away from purist weak coupling idea, but we do it nonetheless. Okay.
Yeah.
So
okay, and sorry to interrupt again, but still, let's say that we consider the case where there is no dynamical quarks. No, you mentioned this, right? And consider this limit of small l, right?
Yeah.
So it's a pure glue. So then boundary conditions for not for Fermions. I mean, the theory itself is gluons, right? So
well, the super partners are there too.
Right,
it's a supersymmetric theory. Yeah.
No, right, but what means supersymmetric theory? So you mean super partners of heavy quarks, or what? Which super partners? Because if you are still using this probe quarks as
no. The probes are, because the probes are heavy. Their spin doesn't matter. Okay, they're just
right. Okay,
the probes are Wilson loops.
Yeah, that's why I'm asking that if I consider just pure glue in the limit of small s1, I would be thinking that it's like high temperature and there is the confinement.
No, the theories in the long distance theory are the U1 to the n-1 gauge bosons. Plus gluinos. This is the theory.
I see. So for you, these Fermions, which are partners of gluons, are important. I got it.
Exactly. Okay. Yes. Those are the dynamical ones. Yes.
Okay.
Yeah.
Okay.
Okay. Cool. It's okay. So that's my plan. Okay. So please continue interrupting. Okay. So finally, I get to describe my theory. Okay. So the long distance theory is a abelian gauge theory. It's an abelian gauge theory in 3 dimensions with no charge fields. Okay. So in the talk, because we're doing classical studies of strings and color fluxes, I will not even talk about the fermions, even though they are important for generating the superpotential, etc. But I will just consider the bosons. Okay. So the bosons are as follows. You can dualize the n-1 photons into dual photon fields. Okay. So these are bosons, and together with the Cartan component of the holonomy, they form a complex field. This is the lowest component of a chiral superfield in 3 dimensions. Okay, so the dual photon together with the Cartan value of the holonomy. Okay?
So you mean it's equivalent of complex scalar, right?
Absolutely, yes. Absolutely, yes. So those are the fields, and the relation to 4-dimensional fields is as follows. As I said, the sigma fields are dual to the Cartan photons. So mu and nu are indices in R3. So the dual photons are the duals to the F mu nu. So F mu nu is the field strength along R1, 2. And the holonomy scalars are just the F mu 3, is the mixed component of the field strength. Okay, and they're fermions as well. Okay, so in this relation, I explained who is who, and G squared is the 4-dimensional super Young-Mills coupling at a scale of order 1 over NL. Okay, that's those are the fields. I will write out the Lagrangian, but the order is such that I write it a little later. Okay, the reason is the following: because I will describe classical fluxes, etc. I just want to interpret these relations, and these relations say this. Remember, the dual photon is the dual of the field strength. So so S1 is the small direction, which we ignore. Y and Z are the 2 space directions, and there is time. Okay. And so everything will be static in what we study. We're studying static configuration. So the electric field in the Z direction is the Y derivative of the dual photon. The electric field in the Y direction is the Z derivative of the dual photon with a minus sign. And similar for the magnetic fields in the Y and Z directions, those are derivatives of this phi. Okay. This is just useful to keep in mind because we want to translate to physics in 4 dimensions. Okay. And because the dual photon, its spatial gradient is a 90-degree rotation of the electric field, if you consider a charge, say, placed here at the origin, and this charge is, say, 2 pi lambda, where lambda is a vector of the u1 to the n-1 charges. If you consider Gauss's law, you consider the integral of E through this, the flux of E through this circle, that is given by the monodromy of the dual photon. So the dual photon field has a monodromy around charges, which is 2 pi lambda. Okay, so that's that. And this is an SUN theory. So in an SUN theory, you can have probes of charges which are in the weight lattice of SUN. So the dual photon is a periodic field, and its periodicity is given by the fundamental weights of SUN. So I'm trying to be general because this is I'm using more than SU2. Okay, so this is the Lagrangian that Arkady was asking. Okay, so this is
but in terms of this charges, when you break into this U1 to n-1, you explain this electric charges, right? Do you have magnetic ones as well?
No, I mean, there are magnetic monopoles, the dynamical magnetic monopoles in the theory.
Yeah. But but it's what I'm asking right about. Yeah, it would not show up.
There are dynamical monopoles which are responsible for generating this object, the superpotential, which I will not describe. I will just declare it. Okay, and I will put it also in a language that may be more familiar. Okay, but so this is the Lagrangian. Let me just say this, okay? So this is simply the dimensional reduction of F mu nu in 4D, okay? Just written in this complex field, okay? And so this is just free electromagnetism written using these dual variables. And this is, of course, U1 to the n-1. This is all it describes. And actually the entire 4D F minus squared. This is the interesting part, and this is the non-perturbative superpotential, which is generated by monopole instantons. Okay, there are many ways to write it, but this way is particularly convenient. There are n terms in it. There are n monopole instantons. They are labeled by the simple roots of SUN, and one of them is labeled by the nth root. So just if you just to remember, there is another way of writing it, which you can write it as a product of n complex variables where there is a constraint that the product is 1. It's an equivalent formulation where these x's are some complex fields which are constrained to be 1. The map from these fields to these fields is the same, but this may be more familiar. Okay, I don't know. Okay.
So Eric, can I ask a question here? So, could you also add a theta term then, and then and then dimensionally reduce that as well to
I
3?
could, but I have massless fermions, so it's not that interesting.
I see.
But
That's
it
very
is
good. Yeah.
possible to study this theory with massive fermions,
I
and
see.
you can write many papers on that, and so we have. But
So that's
this
the
is not what I'm
gluinos.
studying.
Yeah.
That's the
Because you have
gluinos,
massless,
yes.
Yeah, you have the massless
Yeah.
gluinos. The theta is just
Yes,
unphysical.
yes, yeah,
Okay,
exactly,
thanks.
yes,
Yeah,
yeah. So, so look, this superpotential is just an input for me. I will not quite discuss it, but for SU2, this is what Misha was saying. For SU2, this is 1 over x plus x. Okay, it's a familiar thing. Okay, so anyway, so this is all I'm going to say about this. We will use this Lagrangian to calculate things, but this is given. Okay, many people have studied that, Cyber-Quitten first, and Davis, Hollywood, Jose, Mattis, and others, and many people have contributed many things. So what we know exactly is the superpotential is a holomorphic thing. I have conveniently normalized everything, so this is how I define it, dimensionless. M is a non-perturbative scale. It's related to the lambda scale, which I want, right? Okay. And what else do you need to know? Oh yeah, the Keller metric. The Keller metric is known to one loop order. To leading order is just diagonal, which is the very small circle limit. And there are corrections, which I will take into account at some point, okay, towards the end of the talk. Okay, so this is my theory, okay? So I have to tell you a few things about this theory. This theory has n vacua, and that's familiar from the theory on R4. The supersymmetric theory has n vacua. And this vacua we can find by extremizing the superpotential. And there is a formula for this vacua in terms of Lie theoretic terms. In all these vacua, the holonomy is at the center symmetric value. So that's quite interesting. And the dual photon has an expectation value, which is some integer times 1 over n times the Val vector. Okay, so this is very group theoretic, but let me try to illustrate it on SU3. In the case of SU3, I told you the group lattice is 2-dimensional, right? We have SU3 breaks to U1 squared. So there are 2 dual photons, and these dual photons live in this fundamental cell. What is it called? The cell of the weight lattice of the gauge group, which is just this. This should be familiar from the quark model, okay? So this point, this point, this point, and these points are all the same. The dark points are the different vacuum. So there is a vacuum at the origin, a vacuum here, and a vacuum here. These vacua are related by the broken discrete chiral symmetry, which acts on the dual photon in a certain way, okay? So these vacua are what happens from to the n vacua of super Young-Mills when you compactify the theory, okay? They are distinguished by the expectation value of the dual photon, which takes n different values, okay? And what's interesting for me now is...
Eric, I'm sorry, but when you have this complex scalar, right, which is kind of phi plus I sigma, right? There is no phase rotation between them. It is still the U1 to n minus 1 theory, right? Because when you are saying that it is sigma which has vacuum value but not phi, it implies certain kind of, I don't know, constraints or whatever for the phase. That's why I'm asking.
Yeah, the phase rotation of this complex field is not a symmetry.
Yeah, but so you have this peripheral, choice, right? In this sense.
Yeah. It's not a symmetry. Yeah.
Okay.
You see, the superpotential is this. So if you rotate this field by a phase, it's not a symmetry. Yeah. Okay. The shift on sigma, on the other hand, is a symmetry. That's the R symmetry, because it shifts the superpotential by a phase. Yes. So it's correct. Yes. Yeah. It's a. If you write it in superfield terms, I don't want to introduce that. Okay. Yeah. If you write it in superfield terms, the Keller potential is x plus x dagger squared. So it doesn't have the. It's a peculiar choice. Yes. It doesn't have the rephasing. Okay. Okay. So fine. Yeah. So these are the vacuum. So whenever you have discrete vacuum, you have domain walls. This is where I'm headed. Okay. There are domain walls, and there are n vacua. There are domain walls, and there are n vacua. And so if you have n vacua that correspond to the breaking of some Zn symmetry, there is the notion of k-wall. A k-wall is a domain wall that connects vacua k units apart. So it takes sigma 0 to sigma k. And of course, this is a supersymmetric theory. There are BPS domain walls. They obey certain equations, etc. Okay. We will talk about these walls in a little bit more. One comment is that the walls are totally semi-classical. You never exit the effective field theory. So some people are confused by that, but you never strayed very far from the center symmetric expectation value. The center symmetric expectation value for phi is where the gauge symmetry breaks to U1. So the theory stays abelianized all the time. Okay, so phi never strays away from zero. It has to, so in the effective theory, okay? And this is an example of static walls. So say for SU4, just to show you what fields do, for SU4, you consider vacuum 0 and vacuum 1. And the sigma fields do things, okay? There are 3 sigma fields for SU4. They do things like that. They change. And the phi field does something like that because it goes from 0 to 0. What's important is that the static walls are one-dimensional lines. Remember, the space is R2. And I have written a static wall where you go from, as you go traverse the y direction, remember the space is y and z. As you traverse y, the sigma field changes in the y direction. But remember that y direction change of sigma was an electric field in the z direction, in the direction towards me. You don't see my pen, but it's towards me.
No,
so this means,
Eric, maybe I missed. So you say that phi is appears on the wall, or
absolutely, yes. Phi
Yeah.
appears. Phi does something like that. There is phi 1, phi 2, phi 3. Okay,
I
you will
see,
see
okay.
in later plots. Yeah, yeah.
Okay.
So the wall, actually, it's interesting. The wall carries some magnetic field, you know, back and forth. The flux is 0 because remember d phi was magnetic field, right? So there is some flux going this way and some other flux going the other way. It's very interesting. Okay, so, but anyway, so yes, phi appears. Okay, but the point is that along the wall there is an electric field, and so okay, fine. So now something that you guys know quite well. Okay, so you know that in this theory, there is a multiplicity of BPS walls. In particular, if you consider vacuum k units apart, there are n choose k different k walls. And this has been known for quite a while, you know, by even before this probably, you know, in Landau-Ginzburg models, etc. But there are various ways to see that. And it's very interesting that in this small L theory, these n choose k different k walls are distinguished by the electric fluxes they carry. And remember that the sigma field is a field which is defined on a torus. So as you traverse the wall, there could be a monodromy associated with that. And so what happened last year is that with Andrew Cox and Sam Wong, we first numerically found and then have an analytic argument as to the electric fluxes carried by the various walls. Remember that the change of the sigma field is the electric flux. And it turns out that there are n choose k electric fluxes, and there is some formula I will not explain. But the point is this. The point is that if you know the fluxes carried by BPS walls, you can figure out the combinatorics of confining strings of lowest tension that confine quarks. So it's an interesting story. For most of what I will talk about, one walls will be the most important. So let me just illustrate that for the case of one walls, because it's very simple. So for one walls, there n choose 1 is n, and so there are n walls. So the sigma field changes by 2 pi over rho in one wall, 2 pi over rho minus every possible fundamental weights. So for SU3, this is the picture. Remember, this is the sigma field. This is one vacuum. This is the other vacuum. So this is one wall, obviously. And this is another one wall, because this vacuum is the same as this vacuum. So this is another one wall. And this is another one wall. And so there are 3 one walls, which are distinct because they carry the same, they carry different electric fluxes, and they are related in the case k equals to 1 by the unbroken center symmetry along the compact direction. So these walls will be very important for us. Okay, so the physical picture is that there are distinct walls that go between in equivalent vacuum. Okay, and the main difference with the Polyakov model you can see already from this picture. Remember, a fundamental quark has a flux which is in the weight lattice, for example, W1. But our walls, as opposed to the walls in the Polyakov model, carry flux which goes from here to here. So there is no way to have a wall with this flux suspended between fundamental quarks because the flux is wrong. You need at least 2. Okay, so this is the difference with the Polyakov model. So it's quite different. Another difference with Seiberg-Witten model is that because there are n BPS walls, for fundamental QQ bar mesons, they're all degenerate. So all the string tensions for all QQ bar fundamentals are all the same, which is not the case in cyberquotient theory, as Arkady has studied quite a bit. Okay, so that's quite different. So so this is the picture of the wall. I will not use in detail these fluxes, but I will use the one wall fluxes. Okay, so how do I construct? Oh, I have to tell you more. Okay, so now static quarks in this theory are Wilson loops in arbitrary SUN representations. When you abelianize, you can classify the Wilson loops by the weights of the quarks. The weights are just the charges under U1 to the n-1. So the weights take values in the weight lattice of SUN. They're integer linear combination of fundamental weights. Okay, and so there are n weights of the fundamental representation, which I denote is by nu1, nu n. Okay, so these are the n components of the fundamental quark. If I form an Analytic K representation, say of K index, by taking n fundamental quarks together, then the weights are just the sums of all possible combinations of fundamental weights. So these numbers n1 and k all takes values from 1 to n. Okay, so in general there are many different weights of Analytic K for a K index Analytic K representation. Okay, and a very important weight is the kth fundamental weight. The kth fundamental weight is a weight of Analytic K, is the sum of the k first different fundamental weights. It's very special for the following reason. If you have a quark of any weight, you can add or subtract roots, and you can take this weight to the fundamental weights of Analytic K. Physically, what this means is that if you put static sources of some weight lambda of Analytic K, you can pair create W bosons, and these W bosons will screen it down to the kth fundamental weight of SUN. So this weight is very special because we will argue using the combinatorics of the double string mechanism and the properties of W walls that string of Analytic K, the ones with lowest tensions are the ones where the quarks have weights WK. So in other words, this is the highest weight of the K index anti-symmetric representation. Every Analytic K representation is screened by W boson production to this one. Okay, and we will determine this tension in this model, and we study the K dependence. Okay, so that's what we'll do. So how do we do that? Just a couple of words. Well, it's very simple. We add a you do it as in the Polyakov model. We add to the action a term which represents a quark at some position and an anti-quark at some position. These quarks have weight k, and then we turn the crank, and we find the equation of motion that describes the field configuration with this source. So this is the equation of motion that follows from the Lagrangian that I had before, and adding this term in this dual language creates a source term like this. So it looks quite complicated, but if you just remember that this field X was the imaginary part of X was the dual photon, this term that's added only affects the imaginary part. So this term really implies that on the line that connects the two quarks, there is a jump of magnitude 2 pi lambda of the sigma field. So the sigma field has a non-trivial jump, which is in the weight lattice on the line connecting the two quarks. And what we do to find the string tension, we solve this equation numerically, and the papers explain how. Okay, so from now on, I will just use the fact that I need to have this jump of the sigma field as I go on between the two quarks. So now I want, yeah.
Okay, no, just I'm sorry to interrupt, but still, let's say that we are considering the dynamic of the theory, and there is no this external heavy quarks or whatever to probe. Okay.
Yeah.
Then the way I got it from you that it would be like an index of the theory, still with your periodic boundary condition for Fermions.
The partition function would be an index, but you can calculate other things. You could calculate the spectrum of particles. You can calculate, there is an interesting spectrum of particles. There are dual photons.
Yeah,
all kinds of things you can calculate.
So it's not it would not be based on partition function type.
No. You study the effective field theory. Yes, absolutely. Yeah.
Okay, but then you are saying that boundary condition are irrelevant in certain sense, right? To the extent when you're going to the bulk, you could say, aha, it doesn't matter what boundary conditions are there if you're indeed going for spectrum of the particles, right?
No, but it really matters, because if the S1, if the fermions are not periodic, the theory is strongly coupled, as you say. You see?
No, but look, physically, I would say that if I consider some experiment which are far away from, from the boundary, I would be thinking that it doesn't matter what a boundary condition for global.
No, but you see, no, but why are you talking about boundary? Because we have this situation. Here is the S1,
yeah,
and this size is L, okay? And we are considering dynamics in R3 at scales much bigger than L. So
yeah,
to figure out what the effective theory is on R3 at scales much bigger than L, these boundary conditions matter a lot. If the fermions were periodic, anti-periodic in this direction, then this theory is strongly coupled.
Okay, so then you are saying that it's like a different series, right?
Absolutely, yes. Yeah, absolutely. Yeah.
Okay.
Yeah.
Okay. I'm sorry.
Okay. Yeah, no. For what?
No, I'm sorry that I'm interrupting, but look.
No. It's more fun, okay? I have time, okay? All right, look, okay, so now I want to illustrate double string confinement, okay? So I take two quark sources, and these are their charges. Remember, this is the U1 to the n-1 charge. And I'm solving a classical equation of motion. So this is semi-classical theory. So I want to find the field configuration. And the point is that the classical equation of motion tells me that there should be a discontinuity on the line between these two quarks. So I imagine that I place everything in some vacuum, let's say in the zeroth vacuum, okay? So this is the quark, this is the antiquark, and I want to have a jump of the sigma field here, which is given by this 2 pi lambda. So the way I can obtain this is this. Let me say that in here, just above this line, I am in the vacuum, in the kth vacuum, plus some weight vector, and below this line, I am in the kth vacuum plus some other weight vector. And I choose the difference between these two weight vectors to be precisely this weight, so that I'm guaranteed that when I cross this line, the sigma field jump is given by 2 pi lambda. Okay, I do that, so this is fine. So this satisfies the boundary condition. It's vacuum here, and vacuum here. But this vacuum is different from this vacuum. So this means that I have to have a domain wall that connects this part to this part, and another domain wall connecting this part to this part. So there is a vacuum 0 outside and vacuum k inside. There is one domain wall and another domain wall. And now as you go around this source, you get precisely the right monodromy because of the sigma field, because across this domain wall and across this domain wall, the monodromies add up to just be right. Okay, so this is the simplest way to cook up a configuration out of these domain walls, which are where the electric field sits. Remember that the electric field is in the domain wall, the sigma changes this way, so there is an electric flux going this way. So this is the picture. The electric flux is collimated in these thin tubes, which are the lines, which are the domain lines, and in general it's split by 2. Okay, and then we know what the domain walls are. There is a large number of domain wall and vacuum, and the question is which are the ones that have the lowest tension. And if we concentrate on the sources of the kth fundamental weights, that is to say the highest weight of the k-index anti-symmetric representation, so quarks of Analytic k, it is possible to use the 1 walls. I told you that there are n1 walls, and you can use the combinations of these n1 walls. In fact, there are n-1 combinations such that the right monodromy is obtained for the k-index k-index fundamental representation. So I have shifted the vacuum here to be the 1 vacuum outside and the 0 vacuum inside, but it doesn't matter. So you can write such a configuration using 1 walls. Of course, you can use higher BPS walls. So these are 1 BPS 1 walls, 2 different BPS 1 walls, different fluxes, but the same tension. You can also have higher ones, but the point is that all these higher 2 walls, 3 walls, etc., they have higher tension. So you expect that the lowest tension will be the configuration that consists of BPS 1 walls. Okay, so that's what you expect, at least based on simple arguments. Okay, so and of course, as I said, pair production of W bosons expect to screen everywhere, every weight to the first fundamental weight. Okay, so this is the mechanism of confinement, and this is what was conjectured a few years ago. So the moral is this. The moral is that this double string picture and the BPS wall properties imply that quarks of N-ality K are confined, at least in configurations of lowest tension, by BPS1 walls. So this is the main picture. And of course, we need to substantiate this picture because it's a picture. Okay, we need to find out more about these configurations, whether they are realized, et cetera, et cetera. So we need to substantiate that. I just wanted to say one more thing. So if we ignore W boson screening, which is not something that you see in the EFT anyway, we can also do the combinatorics, and we can argue that K-index N-ality K quarks are confined by lowest tension strings, which are made of 2 BPS walls with P less than or equal to K. Okay, it's sort of some amusing taxonomy, but you know that including W bosons, eventually you will screen the walls. You will screen to these BPS1 walls. And in the effective field theory, also gluons are confined. For example, if you take a W boson in SU5 of charges alpha 1, which is in the root lattice, then you get some triple string configuration. It's kind of, this is just for amusement of the picture, but it's well known that the abelian confinement also root charges are confined. But of course, in the full theory, you expect that to go away. So, so in any case, my goal next is to substantiate the picture. And this is
look, but I also wonder that in certain way, once you are talking about these configurations, I would say things that, and you mentioned before, that kind of in terms of a particle-like explanation, you were mentioning, you know, this kind of, you know, kind of monopole solitons, whatever. So there is some kind of spectral stuff in the spectrum which refers to kind of effectively like heavy composite particles, right? Or it's not the way you can associate it with your picture. Remember you mentioned this kind of bias or whatever.
Oh, but the bias, these are Euclidean objects. They're not particles, right? These are some instantonic objects.
Right, I agree. Right, but I'm wondering about indeed kind of particle type object like composite, you know, monopole, say in 4D, right? I mean, would it be something like this in your picture as well present, or nothing like this? No, because
as far as composites, there is one funny thing that Alexei studied quite a bit. there could be very weakly bound states of these dual photons, but this is something very esoteric. Okay, but indeed, I don't want to go there. It's not related to my talk. Okay,
no, because normally
it's a fascinating thing, but I'm sorry. Alexei is laughing.
No, but usually there is this, you know, kind of for kind of barrier penetration as usually associated with existence of something. You know, you have these domain walls, but you can also think that this appearance of stuff like phi on this whatever could signal of existence of some kind of composite particle-like stuff in the picture, but I'm not sure. I just wondering. You see, because you have a different scale, right? You have kind
yeah. So Arkady, yeah, there are some composites that appear, and they were studied by Alexei and collaborators first in non-supersymmetric versions of that, and by Mohammed Anber and myself in the supersymmetric theory. There are some bound states of phi and sigma which are kind of weird, but I don't think they have anything to do with this confinement, at least at face value. Yeah.
Okay, so it's not like monopoles. Right?
No. This concerns the particle spectrum of the theory. So roughly speaking, there is some delta function-like interactions which like to have bound states. Okay, that's really what happens in 2+1 dimensions. And it's really the glue balls in 4 dimensions should map to those. It's very interesting because these sigma particles are charged under this center symmetry along the S1, so they cannot be the 4-dimensional glue balls. The 4D glue balls are some bound states of sigmas. But I don't want, and there is another small scale, you know, it's a sort of a doubly exponential scale. It's very interesting, but I don't think it's related to that right away. Okay. But thank you for asking. Alexei, if you have to say anything, go ahead. No, it's okay. Yeah, okay. All right. So So I told you how we think about these strings. So let's just now see whether these things actually happen. And I've just chosen to show you a few pictures. I won't bother you too much with that. We have a big disk of, you know, is it a terabyte or, well, maybe not, maybe 100 gigabytes of stuff, okay? But I just want to show you, so for SU5, we consider antisymmetric quarks. So the weight is index antisymmetric, and the distance here is taken to be just 15 in units of the heaviest dual photon mass, okay, inverse heaviest dual photon mass. And well, again, for SU5, there are 3 sigmas and 3 phis, okay? Sorry, 4 sigmas and 4 phis. It's too much to show, but I just showed you the third component. So the sigma field behaves like this. So this is a vacuum, and the phi field behaves like this. And so this is the configuration you get. What's interesting is that this configuration, you have this electrostatic problem, and you relax it, you solve it using relaxation. It's independent on the initial configuration. You know, okay, my collaborators tried with completely random configurations. You always relax to this. It's very interesting. And that is precisely what I told you before, that there's going to be a one wall, another vacuum, and a one wall. So this is the vacuum 2. Outside is the vacuum, no, outside is the vacuum 1, inside is the vacuum 0, okay? And the point is that if you look in the middle between the quarks and you study the profile of the sigma field and the phi field, those very strongly resemble what you get for one-dimensional domain walls, which kind of makes sense, because if you take the quarks far apart, you expect that these things will look very much like one walls. So the point is that this picture holds, at least for W2 quarks, and it holds for old colors. It's not something that we have cheated, okay? So this picture is correct, and indeed, it appears that the lowest tangent configuration is the one that has 2 one walls arranged in such configuration. So as I said, relaxation appears to confirm the picture, and this seems to hold for all n. When you say all n, we mean up to 10, okay? For all n, and N-ality k bigger than 1. These walls repel, and they form this double string configuration. For k equals 1, we'll find something, which I'll explain in a moment. But let me first say, how do we characterize the strings? We characterize the strings by these double strings, by the string tension and the string separation. And you expect to have string separations if the wall repel, because, right? Because you want to, on the other hand, you want to minimize the length because it has cause tension. On the other hand, if they repel, they want to separate. So there is some trade-off, which is the D, okay? And so the first thing to note is that the energy of this configuration, we say here that it's approximately linear, but then if you look at the plot, it is linear, okay? So this is for SU4 and N-ality k equal 2. The distances go between 5 and 100 in units of the dual photon mass. And you see that it's a perfect straight line, okay? So, and this was done by changing the radius by 1 unit. And if you look at the value of the string tension and the value of the twice times the BPS one wall string tension, which is something we know exactly, you cannot distinguish them using the accuracy of the numerics, okay? So it's very close. And so you may say that, should it be obvious that the potential is linear in the separation because there is this curvature, etc. So you might say that, you know, maybe it goes like R log R or R plus log R. This option is forbidden by some general ideas. So there is a bound exact result on the lattice that the R cross T Wilson loop, the expectation value of the R cross T Wilson loop is bigger than the recall than the expectation value of the 1/1 Wilson loop to the power RT. So this inequality forbids a potential rising faster than R, because if the potential rises faster than R, eventually this will decay and it will become smaller than the right-hand side. So it's a very interesting inequality derived by these people, okay? I learned about it from Larry Yaffe. So it forbids the potential rising faster than linear, so it's consistent, but of course this is quite consistent, but we cannot see logarithm because
but in this way, you know, how to say, the energy in certain sense is double tension, right? When you have
it's the double wall tension.
Yeah, right. No, but when you are writing this, it's a tension. Your T1 is a tension for one wall, right? It's not.
T is the tension of one wall.
Yeah.
T is the tension of one wall, but the T is 2T on.
Yeah, it's what I was checking, right? Okay.
Yeah. So it appears that linearity is a property of this thing, okay? So, right, very nice. So what about the string separation? Let me just show you a picture. So this is what happens for SU3. Maybe you see, maybe you don't, that as the quarks get further away, oops, the strings separate, okay? And there is a very simple model that we wrote with Mohammed and Tin. Basically, if we model the double string configuration like this, instead of writing this, we model this as a square where the separation is d and the distance between the quarks is r, and we say that the energy is the length plus some repulsion because of repulsion due to the repulsion between these two parallel walls. And minimizing with respect to the distance gives a logarithmic dependence. Okay, so it's a very simple argument. And we can actually measure the separation. So this is the separation for SU5 for N-ality 2. So this is the log, and you can see that it's a perfect fit to the log. It's quite impressive. Now, the separation of these strings depends on N-ality, and there is tables in the paper, so we cannot explain that in the simple SU2 model. But the general fact of a log is actually there. Okay, so that's the string separation. And the most striking thing, which was just unusual, and I don't know what it's telling us, that only for fundamental quarks, the domain walls attract. So you consider a configuration of two different BPS1 walls, and only if they correspond to, are appropriate to confine fundamental quarks, they attract. And what you get is a single flux tube, so everything collapses, and there is no double string structure, okay? So what these walls do is they form a bound state. So this is for SU5 with Analytic K=1. This is the first time this appears. This is twice the BPS string tension, and you see that the string tension here is less. So these walls collapse and they have lower energy than twice the BPS string tension. We don't have an analytic understanding of this, and we spend some time making sure that that's true, okay? So I don't know if people have great ideas of how to study that analytically, but this is what we did. So we did two things. One thing we just considered.
If it would be like a BPS sector, this would be impossible, right? Because
these are not mutually BPS walls, right? Because
I understand. But because otherwise, I mean, it would be
of course
contradiction. Okay.
Yeah. So what we did is we considered the following thing. So we considered we just considered two domain walls arranged so that so we go to one dimension now, because we say that if there is a domain wall collapse, it ought to be that just straight domain walls attract, and that's what we decided to study. So if we go to SU4 and we consider two domain walls that have monodromy to confine quarks of N-ality 1 or quarks of N-ality 2, and we consider their energy as a function of the separation. So these are really kinks in one dimension. If you go far away, the energy, of course, is just twice the BPS wall one energy. And when you bring them together, both energies increase. Okay, so this means they repel. So that's what you expect. If you go to SU5 and any higher SUN, on the other hand, what you find is that if you consider two BPS1 walls such that the total monodromy corresponds to anti-symmetric quarks, they do repel. But if you consider the ones corresponding to fundamental quarks, the energy is decreased as they get close together, okay? Of course, this is the energy of a naive ansatz, which takes two walls and just computes the energy as a function of the separation. So you may say this not necessarily what you should do. So what we did is the analog of a streamline. You know, streamline is a way of finding instanton, anti-instanton configuration. So this is what we did for SU5. So we considered the following thing. We considered, so let me guide you to this picture. So this is a configuration of one wall and then another wall. And this is the initial configuration where we just put two walls separated together. This wall carries this flux. This wall carries this flux. So these are both BPS walls. I'm just showing the phi fields here. And the total flux, of course, is 2 pi W1, as it should be for K for 1. So you start with this initial configuration, and then you just take this as initial data for the relaxation. And then what you find is that these K for 1 walls collapse. The reason they're not taken further away is that if they're further away, the force is so small that you cannot ever make them collapse. So you have to take them pretty close, and then they collapse. So this is the result of the numerical collapse. On the other hand, if you take two walls that such that one wall carries flux 2 pi rho over 5, and sorry, this is just this is the These are both BPS1 walls. So this is a, oh, this should be omega 2. I'm sorry, this should be W2. This is my mistake. I was just typing that today. This should be W2. So right. So if you take these two walls and start with the configurations where on top of each other. So this is a configuration of these two walls taken on top of each other. And then you relax. You say, let me see what the action wants to do. And these walls separate. So for k equal 2, even if you put them on top of each other, they separate. So it's very interesting, and I don't have a simple explanation of how to study this interaction. Notice that this involves 4 phi fields and 4 sigma fields, and everything is a priori nonlinear. So I don't know how to figure out the interaction, but one comment I want to make is some observation which is made by looking at this configuration. I'm showing you the phi fields, but I'm not showing you the sigma field because something strange happens. The sigma field in the relaxed configuration, they actually just add up. It's almost like the sigma fields don't interfere, even though it's a nonlinear system. It's very strange. I don't have an explanation, okay? So anyway, it's a fact. So this is why we believe that this is correct. Why it only happens for k equal 1, it doesn't happen for other walls, I don't know, okay? So basically I told you almost everything. Wonderful, I told you almost everything. And now I can discuss the string tensions and the analytic dependence and our studies of increasing the size of the S1, okay? Wonderful. So the one thing that this mechanism implies right away is that the analytic dependence should be roughly flat. Because you see, all the confining strings for quarks of analytic K are composed of the same BPS1 walls, and BPS1 walls have tension, which is determined by supersymmetry. And the tension is roughly twice the BPS tension, the tension of the string, for all analyties. Only for K equal 1, we have some bound state that forms, so the string tension is smaller. So we expect the string tension to jump between 1 and 2, and then to be approximately flat. Okay, so this is the qualitative explanation, and indeed this is what happens. So what I'm plotting here is the string tension ratio. This is a standard object that people sometimes study. It is the ratio of the K string tension over the 1 string tension. Okay, and I'm plotting it as a function of analyty for the largest gauge group that we did. And so what we find is the lowest curve. So as you see, for strings confining fundamental quarks, the tension is lower, then there's a slight increase and it's approximately flat. And I have plotted other scaling laws. So this ratio is known as the string tension scaling law. And this is lower than any of them. So in MQCD or in cyber-Quitten theory, or as recently argued in small m 2D QCD adjoint, what people argue is that there is a sign law or approximate sign law in cyber-Quitten, for example, and it looks like that. It's very different. So Casimir law calls in another set of theories, and in the MIT bag model or in deformed Yang-Mills at theta not equal to pi, we have what is known as the square root of Casimir law. So this is the flattest string tension that there ever was. Okay, so that's that. I should say one thing. The reason this is kind of interesting is that if you go to R4 and you consider large n, then you can argue based on large n argument that strings should be non-interacting and you expect the string tension to approach K. So you expect it to be linear as a function of analyty. And this is indeed what the sign and the Casimir laws gives. And clearly abelian large n is different. There is many interesting things that can happen in the abelian large n. So you don't expect it to be the same. We can ask now the following question. What happens to the string tensions and the string tension ratio as L increases? I call it the $1 million question. Okay, it's a joke. Okay, whatever. Okay. So how can we study that within this semi-classical theory? So I told you that so far I suppressed all dimensionful parameters. The string tension for the K strings in SUN theory scale like this. So lambda is the 4-dimensional lambda parameter, L is the size of the circle, and lambda Ln is the small parameter, okay? So this is the scaling which you can do based on just dimensional analysis. And T tilde is what the numerical simulation spits out. Now this parameter epsilon is the only parameter that appears in the action. Everything else is fixed by scaling. And this epsilon is g squared n, really g squared n. And using a Kähler metric, which is flat, means that this epsilon is so small that essentially I ignore it. Okay. But really the Kähler metric, there is a correction, which is known, which is epsilon plus something. I will show you what this something is. Okay, so the Kähler metric has some correction. So I can now do my simulation by taking non-zero epsilon. Okay, so if I consider the string tension ratio, then this L cancels out from the ratio. So the only dependence on L on the string tension ratio comes from this correction. So just to show you where this occurs, remember in my theory there was a Kähler potential. So the inverse Kähler metric has this form, and the correction, remember this is g squared n, the correction was calculated a while ago, and the meaning of this correction is that this represents the mixing of the Cartan photons due to W boson loops. Okay, so this is something that can be calculated. And a numerical simulation using non-zero epsilon can be performed. Okay, it is challenging, but I can show you the results. Okay, so ideally what we would expect if you increase the size L is that this curve, at least in the limit of large L, it should approach some of these curves, right? We don't know in R4 in SUN precisely what it is, but you expect that large N arguments hold, and you should approach these curves. Okay, so that's what you expect. Now we calculated this, and what we found is that actually this curve goes down. So what we did is we calculate the string tension ratio for two values of epsilon. So we took epsilon to be 0.1 and 0.009, which corresponds to increasing values of the size of the circle by a factor of 4, roughly speaking. So of course, I cannot assign a definite circle size here because I don't have a control of what epsilon is, but these two are a factor of 4 from each other. So as you increase the size of the circle, this curve actually becomes flatter. Okay, so it goes in the opposite direction, at least in the semi-classical regime, from what you expect. Okay, so what can I say about that? Many things I can say. I can say that maybe the behavior with L of this string tension ratio is not monotonic. Okay, it's possible. Okay, it is possible that the numeric is wrong. These epsilon non-zero simulations are very challenging, and they were not double-checked. Only one of my collaborators, the other had to go to graduate school. So this is what happened. So they're not double-checked. So although I think my collaborators are very careful, but it is a possibility. It's also possible that at this value of epsilon that we took, 0.1, these corrections are not small. Remember, the semi-classical expansion parameter is lambda ln over 2 pi. So in one case, it's 0.1. For the larger dimension, is 0.6. So I don't know whether these chiral corrections are important or not. But on the other hand, the string tensions themselves have a very weak dependence on epsilon. So I don't know what the resolution of this is, but this is the result. Okay. So right. Okay. So I can go to my conclusions and enumerate them. So this theory that I studied is one of only few theories where confinement can be studied analytically. And ultimately, it is the mechanism of confinement that makes this property so unusual. Okay. In particular, this unusual N-ality dependence is something that we haven't seen before. Okay. So we analyzed it in detail. We verified that double string is indeed what happens, apart from fundamental strings. Okay. I don't know why this happens and why it only happens for fundamental strings. Maybe it happens if you increase n past 20. Maybe it happens for other strings. We don't know. But that's what happens. And all of these stories lead to linear confinement. Finally, the N-ality is weakest ever seen. And upon increasing L, this K dependence flattens, suggesting maybe that behavior is non-monotonic. I just should point out that the curvature increases. It's not so flat anymore. I don't know what that means, okay, at least on this scale. If you plot it here, it's going to be very hard to see because these two curves have to be fitted down here. So, I don't know what this means. So maybe a diabatic continuity is not monotonic, and clearly one needs further checks and lattice studies. And of course, one could do similar studies for the Fourier mills at theta equal pi and adjoint QCD. I don't know whether there are any surprises or not. And so finally, there are some other somewhat related questions, which are less into the numeric and the properties of confining strings, such as the world volume TQFTs on K-walls and understanding the appearance of anionic nature of probe quarks from semi-classic. So this is something that has been bothering me for a while, and I still don't know the answer. So this is all I had to say. Thank you. And my message is to study the color field. So
I don't know. Okay, again, I'd like to ask in some kind of physical picture, because what you are, when I try to ask you about, remember this being far from the boundary by this particular periodic boundary condition, I believe I got your answer, that in certain sense I could say that in terms of circle, you're never far from the boundary, because your L is much larger than size of the circle, right? And my view of this is the following: that you see what's going on when you have periodic boundary condition. It gives you cancellation between, say, loops of, say, gluons and fermions, right? I mean,
yes.
boson and fermions. And it is the reason why you can get a, say, weak coupling, because you indeed have a kind of, weakly coupled UN, right? But so in this sense, it's not like original, and it also fits what you said about G. Remember at the end that G becomes effectively small, when you calculate it. So it fits this picture, right? That, but no, I would say that physically it's very much different, because normally we are thinking that at short distances we have kind of original quarks and gluons, and and we know that it is kind of normal, running alpha, whatever, right? I mean, alpha S, whatever. Okay. In your circumstances is not the case, right? Because in certain sense it's very different theory, because you kind of cancel out, kind of three simple loops which were leading to large coupling. Strong coupling does not occur anymore, right? I mean,
correct. It's correct. Yeah, it's
right.
correct.
So in this way, I would say that it's a physics of very different objects. So essentially, you are discussing physics of. No, I am not talking about probes. I'm talking about the dynamical
Yeah, I understand.
part.
Yes, of course.
Yeah,
yes.
right. Okay, and it's very much. I'm not trying to say that it's not interesting. It's interesting, right? But it is kind of far away from picture where you started from kind of known interaction at short distances, and then trying to find out what's going on. So you are kind of, in certain sense, you are jumping to a very different circumstances when you are doing this pattern of which you are doing. Okay, so I'm not sure why I'm asking this, but no, I'm just trying to get a picture of what's going on.
No, I agree that it's different. The coupling is frozen. Yes, I mean that's indeed that the case, right? So yes, so it's correct.
Right. So in this way, it's like in certain sense, it's effectively like a new type of theory of different physical objects, right? Because now, if I'm talking about in terms of, say, dynamics in R3, whatever, then okay, I can talk it, but then I can say that you introduce this new type of objects, and you are discussing how, because this influence of your boundaries, right?
Yes.
Then you're discussing how these new objects, what's going on with them. Okay.
Yes. I agree with that. But look, I said it from the very beginning. Yeah, absolutely. Yeah, that's correct. Yes, that's correct. But still, the two regimes are continuously connected somehow. There is a lot of common with the theories, right? Both the small L theory and the large L theory are confining.
No,
I can break chiral symmetry. So those are very interesting properties. Yes.
No, I agree with this. So I mean, in this way, I agree that even if it's kind of far away from the short distance interaction, it's still very much interesting that you can get these results. Yeah.
Yes. Okay. So yeah.
So Erich, I had a question about your this ratio that you said was flattening out. I mean, can you understand then the asymptotic limit? I mean, does it actually become just flat
when n goes to infinity?
No, you were talking about this.
Well, asymptotic means
ratio.
what?
as L goes to 0, right?
I don't think it's L that makes it go
Wait,
flat. It
okay,
would be N.
let's.
It was N, sorry, yeah, as N goes
Are you
to,
talking about the F of K N ratio?
yeah. I mean, you were saying that it's the opposite behavior that you expected. So does the
Oh,
but it looks like it's just going to go from 1 to 1. Does it just become flat in the end? Yeah.
Okay, okay, so what I was saying is that just based on some circumstantial arguments, I expect that this curve should go to this curve when I take L to be large.
Yeah, but you don't find that. You find the opposite behavior. And
I
I'm
find the opposite,
asking
yes.
whether
Yeah.
you can understand. It looks like it's just going to be constant between, like it doesn't vary at all.
Well, the thing is that you know, I wanted to be careful and honest. Okay, so so say suppose this is for some value L1, and then I consider L2 like this.
Yeah.
The problem is that at some point I cannot compute this curve because I lose the semi-classical approximation. You see, I tried to keep L1 and L2 such that L lambda n is less than 2 pi.
Yeah, but my point is that
yeah,
you don't have much room there, right? It looks like it's just going to be flat. So then does that make sense? And would that ratio not depend on the N-ality then? Does that make sense for that to be? Would the ratio be
within the physics of this mechanism, it does. It is qualitatively expected that it doesn't depend much.
Yeah, because you actually explained it, saying that it is kind of based on this one wall, right? So
exactly,
that's why it doesn't depend on N so very much.
Yes, so you actually expect this asymptotic behavior to be exactly flat then.
Asymptotic in what do you mean?
Well,
in L?
In L.
Changing from, no, I expect it to be this.
Oh, okay.
You see, at some point this should turn up, okay? But there is no reliable way in which I can follow it, okay? Which is what Arkady was saying, because eventually I have strong coupling, okay? But still, it's quite interesting. And the problem is we don't have a qualitative understanding of this, okay? It's based on numerics that you have to trust, okay? But that's what we find. And Matthew, who did that, is a very careful guy, okay? So that's all I can say, yeah.
I ask a question as well. So naively, to really define what a string tension, you want to take an arbitrarily long distance between test charges, larger than any scale in the problem. And this is, of course, very difficult to do here, because if you make the distance too large, you get doubly boson pair production on the string, and you don't know what to do with that. But so all of this, as you said earlier, was in the limit where that doesn't happen. So the distance between test charges is large, but not too large.
No,
do you have any?
No, can I say something? So so if I take the string very large, provided it's in the quarks are in the analytic in the highest the highest weight of the anti-symmetric, you don't expect W bosons to lower the string tension. So yes, there could be pair production, but they won't lower the energy. So why would they even happen? You see? So, right? I mean, that's what I was trying to say, that it's not energetically favorable, right? I don't know, does it make sense?
A little bit confused. I mean, deep in the abelianized regime, I thought it was known that unless you take into account doubly boson pair production in general, you'll get the wrong dependence on the N-ality, like qualitatively wrong. So you need that pair production, don't you? Eventually,
but
to have a dependence only on N-ality and not on the representation of the test charges.
Yes, but my understanding of that is that once you yes, but this pair production will not happen for the anti-symmetric quarks. So I see.
Okay, but they will for other representations. So
for other representations, yes, yeah. But all of this is just plotted for when I say T of nk, I really mean WK in the abelian theory.
Right.
So, right. Yes, that's all I can say.
I have one other question, which I think you might have wrote on your conclusions as one of the things you were trying to understand anyway, which is, do you know if something lives on these domain walls? Is there some interesting degrees of freedom localized in the domain walls?
Apart from the Goldstone modes and the super partner, I don't think so. No. So this, at least in this abelian regime. Okay, so in the non-abelian regime, people write these TQFTs, but the way we understand them here, that is just the multiplicity of abelian domain walls. I don't have a very deep understanding of that, but at least semi-classically, there is a massless Goldstone and a massless Goldstino. That's it, because the wall is have BPS. And of course, there is, it being a, there is all kinds of excitations of order, whatever the dual photon mass or something, okay, which we don't know.
I see. Very interesting.
So, yeah, that's that.
Yeah, so I have a naive question. You said you only observe this domain wall collapsing for the fermions in the fundamental representation. I'm wondering how strong is that statement? What are the other representations you've checked for the fermions?
Oh, we checked for all SUNs up till 10, all N-alities. So yeah. So for SUN, all representations up to, okay. Look,
oh, sorry. Maybe let me ask more directly.
I can give a look. There is an infinite number of representations. Okay, because you can have a symmetric representation with as many indices as you want. Okay, there is no way to check anything for those, but we have done a reasonable check. So first of all, among the anti-symmetric representation, it is correct that among the anti-symmetric representation, only the N-ality walls collapse. If you consider not anti-symmetric, non-zero N-ality representation, within the effective theory, they always have a higher string tension. So that follows from the double string picture. It also follows from some numerics. Okay, so that's the extent of what we know. Right. If you ask some arbitrary representation, if you assume the double wall picture, of course, or rather multi-wall picture, because in general, for a very large symmetric representation, you expect to have many walls, not just one. So that's going to have some huge tension, and it will decay to some of these. But of course, describing the decay, I don't know. So so that's the statement. Yeah.
Yeah. Thanks.
So again, so basically the point is that when L gets very large, how much of this will survive then, do you expect? I mean, these double strings.
Yeah. When this breaks, I enter the regime that Arkady told me I should be studying.
You should what, sorry?
I should be studying.
Oh.
Yes. No, indeed, but I don't know how. Yes.
But do you expect that these double strings could even exist in large and just regular QCD?
Honestly, I doubt it. Yes, I doubt it. Yes, yeah.
I see. So it's really just a property of the 3D limit.
It's a property of this. Yes, it's a property of the smaller. Absolutely.
But I'm not sure. I mean, I should say nobody has ever studied on the lattice, so far as I know, K strings in super Yang-Mills theory.
It's true. You could imagine in 4 dimensions to have a situation like this. I'm trying to do a 3-dimensional picture now, where the string is made out of a 4-dimensional domain wall as there is a different vacuum inside. Okay, you could imagine that.
Yeah.
But I can imagine all kinds of things,
Yeah, no, but it's if you would try to try it in starting from 4 dimensions on the lattice, for example, then you see it would, how to imitate this periodic boundary condition of the circle, right? Let's say that
it's very easy. You just do it.
On the lattice, everything is
you just do it. You just do it, right?
Yes.
No, right. No, but I mean that then you are immediately in very different theory as compared with original theory, right?
Because, no.
Why?
Why?
No, because if your circle is small radius and you have periodic boundary condition, then it's a different physics.
Yes, but when the circle is large, it's not so different, right?
Yeah,
and we're talking about the circle being large.
No. But then when the circle is large, then those objects which Erich is discussing, those objects do not exist. So in this way, this weak Kaupen domain walls exist only because of circle is small radius as compared with
the weak coupling, yes, but there are domain walls on R4 as well. We believe,
of course.
right?
I agree. But I mean, but it's I think it's not. Look, as I did try to say, that this cancellation of say. Bosonic and fermionic loops contribution occurs due to this particular feature, and in this way you are kind of clearing up your short distance interaction with this when the circle is small. I mean, then you do not have strong interaction. Not strong. It's at short distances. It's not a strong interaction, weak interaction. But you are still sitting at a very kind of, I don't know. So technically, you are still, as you mentioned. Remember that your G is small, right? I mean,
yes.
And that's why it's not only small at short distances; it's small more or less all the way for you.
Correct. Yes, it's correct. Yes.
Right. And then to go to the picture where it stopped to be small, right? I mean, where it started to enlarge. This would be this transition between your picture and
Correct. Yes. Correct. Yes.
And it is difficult indeed. I mean, I think it's not easy.
No, I'm not saying it is. Yes. Yeah. But anyway, that's what we find. Okay. Okay. So, Alexei, I don't know if we are in agreement with this WK. Okay. So what you seem to be saying that even if I have quarks in this K index antisymmetric, and I consider the EFT and I take them very far apart, you're saying that W boson production will somehow affect things?
I'm not sure that I'm saying something as coherent as that. I just mean that you could also take quarks in a 2-index symmetric, right? And somehow
for them
you should only have yes.
For them it will affect things, yes, but it's an energy argument. Other than the energy argument, I don't have anything else to say. So yeah, if you take the symmetric, absolutely, you expect a pair production of W bosons to really, they bind to this and they give you this. Yes. Yeah.
Right. So because you shouldn't have a dependence on the representation, only on the anality of the representation.
Correct. Yes. So right, but I don't know how to incorporate the W bosons.
Yeah, I know. Nobody seems to know.
Okay, so that's true. Yes. Yeah.
And like I dimly remember that in what little I know about string theory, when people talk about d-brane interactions, people usually have some picture that they exchange some stuff, and that's where the forces between d-branes come from.
Yes.
Is there any simple picture like that here, where you can characterize like what are the two domain walls exchanging and how do they couple?
This is the problem. You see, in the case of it's a very good question. The problem is that this SU2 model that we did with Tin and Mohammed. So this story, this was based on the following thing. If you consider this as kinks, and indeed in the SU2 theory, these are two Sine-Gordon kinks. This is really all there is.
Yeah.
And we know how Sine-Gordon kinks interact. But Sine-Gordon kinks interact because of exchange of the massive, in this case, sigma field.
Yeah, that's right. Yeah.
In this SUN theory, SU5, you have 8. For SU5, you have 8 massive fields.
Yes.
So I don't know how to think about that.
It's kind of complicated. Yeah, I see.
I can say it's complicated. So we get these results, and it's quite consistent. And the sigma field, the amazing thing is that the sigma field just adds up. You see that the phi fields, there is some wiggles. It's not just the sum. The phi fields is more complicated after the relaxation, but the sigma is really just they almost pass to each other. And I put this comment just because it's there. A scalar theory with a potential equal to our superpotential. So a complex potential, which is equal to the superpotential, is called a complex affine Toda, is apparently integrable. So there is something strange going on, but I don't know enough. Okay.
Interesting. I see.
So yeah, that's all I can say. So it's kind of an experiment. It's not what I usually do.
It's very interesting. It would be really great if lattice folks who compute string tensions for a living could examine n=1 super Yang-Mills and actually make some pictures of what confining strings look like the way people have done for actual QCD or pure Yang-Mills theory more precisely.
For pure Yang-Mills, yeah.
For pure Yang-Mills. It would be really interesting to just plot from lattice simulations, like what does it look like? Does it look like just a single tube, or is it more complicated?
But you mean in 4D, not
in 4D? Yeah,
4D, yes,
exactly. Take the limit where there's all the circles. Lattice is always anyway in a torus, but make the torus big and study a flux tube. Like, what does it look like in super Yang-Mills? Or near, like with, what does it look like on the lattice? I don't think, to my knowledge, nobody's drawn these pictures, and it would be really interesting to see what they look like. Given that this analytic result suggests that weird things can happen, so maybe weird things happen already on R4. We just don't know.
Yeah, I don't know. Having the quarks exactly massless is a bit of a challenge.
Right.
So maybe this stuff can be redone with masses for the Giginos. But then, of course, a lot of this picture will collapse. But some of it can be done if the mass is appropriately small. But I haven't thought of it. Okay, yeah.
But also that say like in this approach by Zyberg, for example, when they are studying different supersymmetric theory, you could see that influence of this massless Fermion there was crucial, right? So in this way, it's an analytical statement that there is a kind of this that it's not just simple bosonic picture which goes in case of supersymmetric series. So to this extent, it's no, right?
Yes.
Very interesting.
Okay, that's my story. Okay, so it's really the life of two undergraduates all summer, all COVID summer. Okay, they had nothing else to do, so.
Actually, can I ask a question?
Yeah.
So I was wondering about baryons in this picture. Can you simulate having 3 probe quarks and see
yes,
what
I
kind
will
of
show you a
configuration
picture.
comes up?
Yes, I will show a picture that exists. It's it's what you expect because the quarks are static. There. So the left is super Yang-Mills, SU3. The right is deformed Yang-Mills at theta = 0. Okay. It goes from delta to Y, and it's there is the reference. Okay. Yes, yeah, but these are static baryons. Okay, so presumably of relevance to some very excited baryon. Okay.
Right, and this the delta in this caption is not the delta baryon, just to be clear, right? It's
no, it's not the delta. It's a you see people
delta shaped baryon.
Yeah, people discussing QCD whether it's a delta or Y, right? They have potential models.
Yeah.
Like Nathan Isger and Patton did that in the 80s. So yeah, so you can have either one, but the one on the left is the natural one in super Yang-Mills.
But I believe that people long ago in QCD they had some argument in favor of this Y shape, not delta shape.
Well, that's the Y shape, the one on the right, right?
It's consistent, Arkady, because the picture with the Y, that's what you would get as you get towards QCD, which doesn't have any light gluinos.
Yes.
Right. And the other thing is really weird. It's the one where you have light gluinos, and our intuition might not be right. So
yes.
Yeah. I have to teach, so I have to run away.
Okay. But anyway, thank you very much. It was very informative. Arkady, yes, I'm sorry. It's not the real world, I know, but I started with that, I'm sorry,
no, but look, I'm not sure that we are living in the real world, so it's okay.
Yeah. Okay. Okay. Well, thank you, guys. If there's any more questions, continue. I have time.
I'm gonna disappear. Bye bye.
Yeah. Okay. Bye.
Okay, thanks, Eric. Thanks.
Yeah,
You're
thank you.
welcome, Tony.
Bye.
Yes. Okay. Thank
Nice
you.
to
Thank
see you.
Thank
everybody.
you so much.
Bye bye. Thank you. Yes.
Bye.
Thank you. Okay.